Hello, everybody, and welcome to episode 4 of Evans Imagines. This is about interpretations of time, introduction to general relativity. Thank you for joining me. You should like this video right below. Make sure you subscribe to the channel so you know when there's another episode or when I'm going live, if I ever decide to do that. We'll see if I figure out the lighting exactly the way I want it. But for now, this is fun. You can see me about as well as I want you to. Okay, so reviewing the homework from last time, just in case you wanted to do the homework, you're going above and beyond. So you're supposed to read chapters 1 and 3 from the Feynman lectures. Skipping the one on statistical physics. Hope you did. Oh yeah, the important thing you're supposed to see there was him citing ML Good. So we'll go over that in class amongst his other objections. But it's crazy, right? How quickly he talks about antimatter having negative mass. It's like page 2 or 3. So that was the main point you're supposed to encounter. To him, it was a core issue. And to me, it's a core issue. And it should be a core issue to you too. Second question, I mean, there's other stuff in there. We'll get to a little bit more from chapters 1 and 3. You're mostly supposed to see how he likes to reason. What he reasons is secondary. Then I wanted you to derive the mass energy equivalence from the Dirac equation norm. So assuming that starting point, I wanted you to provide the positive or negative, see where it comes from, see what I'm talking about. And to see the absolute value sign, maybe you had to go check a physics book or something, but you've checked the physics book now, you know what's up. So yeah, you've found the positive, negative, absolute value sign. M, you know where it comes from. Maybe you've seen the related equation for a no mass thing with momentum. Has the absolute value on the P. Let's see. Got the absolute value M, could have an e to the I theta, not just a negative. That's a point Grammy likes. Oh yeah, so number 3 explains Sakharov's philosophical resolution. So you don't just have the Feynman-Stuckelberg backwards in time stuff. You also have the idea that everything moves backwards in time. That there's an entire universe of things moving backwards in time that's parallel to this one. That was Sakharov's contribution. It's pretty nice philosophically, but it's just that philosophical because we live in this universe. So I don't like completions of this universe that are outside of this universe or outside of my measurement ability, which who knows if that's a reasonable bias, but it's my bias. Then let's see, explain the chemist's concept of microscopic right. So this last one's just kind of a lark. I'm not sure if I still am on this particular tack as much as I was when I first wrote these questions. But yeah, the basic idea here is that there's other times in chemistry and physics we talk about stuff moving backwards in time. Maybe the backwards in time apparent motion can be related to those sorts of solutions better than this current idea where stuff actually physically really does move backwards in time. And we're just so lucky to meet it right here where we exist now. Okay, so now I'm going to share screen. We're going to go in with this lecture. Get into the meat of it. So welcome to Evans Imagines, present. Okay, so yeah, we just got done with the homework from last time. Oh, right, we're gonna go over his dismissal of antimatter. Yeah, nobody else is doing the third thing or the fourth question I asked you, so congratulations, I've tricked you into doing some research. And here's a little bit more about that. So time reversibility. It's when we see CP symmetry, right? CPT symmetry. We expect things to be the same forwards and backwards. And the only way we know whether we're going forwards and backwards is by being there. So that's what this is saying in so many different ways. It's the T in CPT symmetry. And even when CP symmetry is violated, T is assumed to be fine. But yeah, the macroscopic solutions are kind of the other thing that I was talking about and calling detailed balance. Are the Onsager reciprocal relations. I don't know why everybody got to put a name on it. A guy invented it, fine. But detailed balance is nicer. It's a thermodynamic relationship between rate constants, you know, all these are other words. So let's stick with those words. We don't need Lars. Great. Congratulations to Lars. Okay, you know, obviously I want my name to be remembered, but let's remember the real stuff. Graviton, spin 2, antimatter, negative mass. That's important. You can remember me later. Go to my tombstone or something, play a record, maybe play this. That's fun. Okay, so yeah, so that's why I'm thinking maybe these negative energy states, instead of being real things that are moving backwards in time, instead of being antimatter, because right in my telling of things, you have the absolute value, so you don't have these states moving backwards in time. They're all moving forwards in time. But maybe you still have the solutions. I'm not sure about whether or not the negative solutions are real still. And yeah, if you are, send me an email and you can win a prize. I'll win it with you, whatever. Okay, so don't worry, we have more questions though. So if you didn't solve this one, it's not your last chance. There's a lot of low-hanging fruit when you're considering something about the world for the first time. So let's go over Feynman's objections. He is the guy who invented the graviton, plus or minus, and so he gets into it. Pages 3 and 5 of his 2.5 of his book on all of gravity are talking about why this specific idea is wrong. So he wrote a book about gravity and started talking about negative mass antimatter on page 3. So I would say that's an appropriate time to be talking about it. But man, he's got to listen. We're going to listen to that intuition, even where he didn't. So, okay, first of all, I couldn't figure out what he meant. The very first thing he talked about, binding energies of K electrons. I think he's trying to figure out at the time what would have been the largest or like the best Eotvos experiment, like the highest, accuracy they had at the time. But, that's fine. That is only absolute values being proven, that the absolute value of the inertial mass is equal to the gravitational mass. So it's not a good counterpoint. You can do this for homework if you want. I don't think I even, I didn't assign it. You can do that though. Pretty easy. Think about it. Photons are their own antiparticles that are deflected by the sun. This is something we got to think about. I don't know. This is, like I say, topology and me don't feel great together. Counterpoint. The mass is 0. So negative of 0 is 0. We don't really have a problem. The effective masses are still positive because we have that energy is positive in our universe. We don't have a negative energy sea of magical stuff that's full. That comes out only when we conveniently need it for math. And number 4, I couldn't, just like with number 1, I'm not sure exactly what he meant. Virtual pairs and how they are a problem. I guess for me, it's not a theoretical problem because they have no net mass. So sure, have a virtual pair wherever you want. There's negative mass. So, I mean, with negative mass, I guess the problem is if you don't have negative mass, then the existence of virtual pairs is an existence of an additional mass there. So, but the thing I want to call out here is that this is 1964. He calls out the most direct evidence we have that antimatter does have negative mass, that doesn't have negative mass. And then it's the next year proven wrong. So it's pretty wild to me that, 1964 happens, 1965 happens, they find out the CP violated. Nobody comes back until me now making this point. So Feynman suggested on page 6 something I did. Congratulations. Since the gravitational field implies a force, you can integrate arbitrarily far away from the Earth until you find the CP violation that you've observed. So yeah, assuming that you keep finding stuff, eventually you get the field, and it's not an absolute field. So he fixed ML Good, the problem that people hated ML Good, not hated, but the reason they didn't like ML Good's model, he fixed it. And as a result, that's fine. But if it finds stuff as far away, maybe it's too convenient and you definitely can't. Don't have experimental evidence for it yet. But okay, I'm gonna keep going with this. Quantum field theory, let's see. Yeah, I wanted to go over this. Is a very nice, clever thing he does there and that he's done it elsewhere. He likes to separate spaces into complete subsets of the space. So whenever you do a proper ordering of a space like this, it's a very clever thing to do. It's mathematically perfect and it can be conceptually very beautiful. Separating a space into, for instance, forces considered and ones that are external to consideration. Which seems, it's arbitrary, right? This kind of thing in one sense. But if you break it into just the right pieces, it's just like in algebra class, right? Like, yeah, sure, all the stuff is true always, but you do some of the stuff sometimes because it breaks it into a nice little trick, like you complete the square, or you rationalize the denominator or whatever, combine fractions, that sort of thing. So yeah, we're going to use that sort of elegant thinking right now. I think it's what I'm leading up to. I don't remember exactly what the next slide is, so we'll find out together. Yeah, so you guys can develop stuff into conference type things if you want to. Go ahead. Lots of good topics. We can split up the universe into a lot of different pieces. So for instance, we could do our galaxy and the rest, or our galaxy cluster and the rest. These are our arbitrary choices that are nonetheless proper orderings that apply anywhere in the universe. Anywhere has its galaxy, anywhere has its galaxy cluster, right? So it's mathematically perfect, mathematically precise, and one of them can be physically right. I don't know which one's right. I think it's kind of suggestive that the cluster is described as the largest gravitationally bound unit, but I don't know. That's a lot of data y'all are interpreting, and a lot of different assumptions going into that interpretations. Could be galaxies. That's where I've been. That's where we've been pretty much. Intergalactic space is like the furthest we've been. So yeah, my main point, the rest of the stuff is pretty far away. So here's one of my simple ideas that I like, that I think you guys should like too. It's called basically far, I don't know if I have it here yet, but the furthest, yeah, once we split the universe into the stuff we were considering and the stuff external, we can also assume the external stuff's really far. So pretty simple. And it is really far. You look up there, it looks pretty far away, right? A lot of black stuff between here and there. I've been using megaparsecs, but that's just because it's like 1 to 5 of those, right? I mean, it's a nice countable number. You can use light years, whatever word you want. I like whatever is 1, so I'm going to do that. So to me, my point was, since it's all very far away, we're probably feeling an average field from it, right? Like the idea is something moves over there and we go, boop, some sort of weird thing like that. Probably not going to exactly be true. It's very far away. And yeah, so well, depending on how we can get a slightly better version of this argument, if you would like, send me an email. But yeah, you wouldn't expect to find every tiny movement having some sort of ripple later on. Even where you do expect the butterfly effect, you don't expect like some sort of mega butterfly effect Rudolph time. Wow, I mean, maybe you do, I don't know. But kind of makes sense to me because we didn't even see any gravitational waves at all until there was a huge merger of black holes or something, like, right, a really big event. So yeah, apparently there's not big ripples coming through here all the time that are, big, or else we would have seen them. So that's a little hand wave, that, a little bit of a trick, a little circular. I shouldn't celebrate too much of that. But we can do a cool trick with this mean field idea, with this furthest away nearest neighbors. And we can take the Einstein's equation without the cosmological constant. For homework, you can figure out what all of these words mean, and change the range of consideration for the Lagrangian, because Einstein only explicitly considered the mass source. You can see in Hilbert's derivation a slightly different way of going about this. But either way, and if you consider also antimatter Lagrangian, you get, maybe if you pop in a cosmological constant, that's the result of including properly a very far away antimatter source, right? So that's a pretty simple idea, even though the math, obviously, it's tough. A lot of tensors here. You guys are probably scared of tensors. And yeah, you don't need to do this math to understand why I'm right. So if you want to do the math, fine. If you want to tell me why it's wrong, that's also fine. But I'd rather you tell me why it's right. So yeah, this is my take on Einstein. He introduced the cosmological constant to make space flat. That was the wrong fixing it, right? But if you move it to the other side of the equation, now he's right, because now instead of making space flat, you're saying everything comes from nothing, and nothing has no curvature. That statement is less a stretch than the universe is flat, that nothing has no curvature. So yeah, anyway, we have a solution to the fine-tuning problem, why there should be a cosmological constant if it's so small. And it's the result of an integral identity. So I don't know if you could have expected anything better. You've maintained symmetry. A lot of things people like as physicists, a lot of things people like as people, symmetry. Okay, so reflecting on the equivalence principle here. Yeah, the usual formulation of the equivalence principle immediately starts talking about non-gravitational forces. That should be your clue, that we can just extend it to gravitational forces and get a better one, right? But everybody likes Einstein, so whatever. The idea is, aside from gravitational forces, all accelerating frames can't be distinguished from gravity. I mean, aside from gravity, which couldn't be anything more to look at there, right? I propose we should simply include gravitational force, so you don't know whether or not there's positive gravity from or whether you're being pulled to a planet or pushed from an anti-planet. Until, I mean, obviously you have the history of your life, you know you took off from a planet. That's how you know, right, in real life. But assuming that you were one of Einstein's like imaginary dudes in an elevator that has no history or life except, I guess, is living some sort of Black Mirror type physics experiment. That's kind of fun to think about. We should develop that. Okay, but yeah, people have previously said space-time is bent toward mass. We should say that's a real stretch. So maybe that's true, but yeah. Like I say, the interaction of charge and field separately. Nobody would call themselves negative mass. There's a good point. A lot of long words here that are going to be boring even to a physicist. So I'm going to spare you some of these words on the slide. Oh yeah, thinking about, remember in electromagnetism, you had something similar happen where kind of our first step towards electroweak theory, you have the reduction to a scalar potential and the vector field. And so, yeah, why not consider this similarly in gravity? Oh, good. I was getting tired of doing this. So yeah, I was like, when does this end? I thought I had wrapped up this lecture around now. So we have now gotten to the end of the stuff for this lecture. And here are your homework questions for next time. What does the Eotvos experiment establish? And on what domain? So read about it. You can Google it. It's fine. Wikipedia is good. It's a good source. It's better than Encyclopedia Britannicas I grew up with. Then read through Einstein's derivation of the field equations. If possible, expand the Lagrangian to include antimatter. So do the thing I just, I was kind of hinting at there. Read Feynman's quantum theory of gravitation. This is a paper, but it's nice, pretty clear. I think through the establishment of the spin 2 nature, it gets really complicated after that, but it's pretty non-technical up until that point. Read this classic paper by Glashow. It's the same one from Salam and Weinberg. Thus, how I know he doesn't agree with me. Name a fatal flaw to their argument, though. He doesn't consider everything. This is the 90s after all. Then read Nieto and Goldman, because it's the 90s. We're getting caught up on all our classics of negative mass. We're going to go over all these classics of negative mass, antimatter, next time. So thank you all for joining me for this Evans Imagines. And yeah, see y'all next time. Make sure to subscribe and yeah, share also. All right. Have a good one, guys. Bye-bye.